Welcome to the Virtual Foundry podcast.
Hi, everybody, and welcome to the Virtual Foundry podcast. This is volume 5, episode 1. Today is Friday, January 5th, 2024. The time is 2:58 in the afternoon. The temperature today is 36 degrees Fahrenheit. That's a whole 2 degrees for you Celsius users. Winter is in full swing. It's just going to get colder over the next several days as we head into mid-January here. Pretty normal stuff around southern Wisconsin. Today, we're going to be talking about why FFF Metal is important. Now, I'm Tricia Cease, president of the Virtual Foundry, and with me, as always, is Brad Woods, founder, inventor, and all-around science guy. Say hello, Brad.
Hi, everybody.
Now, Brad, if people have been following along, they may notice that our backgrounds are different. I've lost my navy blue wall, and you are definitely not in what we've seen as your lab over the past many videos. What's up?
Yeah, I'm actually in an office now, and I have a wall behind me.
So we just moved. We are in our new place as of January 1st, and it's been a terrific move for the Virtual Foundry. And we look forward to expanding into this new space as we go and working with you. Now, we're talking about why is FF metal important? Now, FFF metal, or fused filament fabrication metal, is metal that you 3D print on your regular off-the-shelf 3D printer like your Creality, Ultimaker, Bambu Lab, and then you heat the printed part in a regular standard kiln to remove the binder that's holding the metal powder together, and then sinter those metal particles together to give you a full metal object on common off-the-shelf equipment. But why is this important? Well, let's go back to the beginning, to where it all started. Brad, as you were putting this idea together and developing these 3D printable filament materials, why did you think that this project was important?
Two things. My first thought was, so I got a PrinterBot Simple, one of the first affordable 3D printers. I printed some pieces, and I found the plastic to be disappointing. It was incredible that you could go from a digital file to a physical object. This was groundbreaking. But it was almost immediately apparent that materials were the next issue. And at this time, a lot of people started businesses built around making 3D printers. And I considered this at the time, but realized that it was more important to focus on the materials. So that's where I went. And up to that point, so the word, the Virtual Foundry, I actually started using this 24 years ago now. It was around the year 2000, and I was developing methods of fabricating metal parts that didn't require a foundry. And at the time, my focus was on electrolysis, so electroforming, electroplating, things coming from that strategy, methods of chemically breaking down metals and reassembling them rather than using heat and melting them and casting them. So step one was I started taking my plastic 3D prints and then electroplating them. And this was interesting, and it gave you some of the properties of a metal part, but not enough of it to be significant. So I had also been experimenting with different types of powder metallurgy, specifically precious metal clays. And these started coming out in the 80s. And they were kind of what I'm describing. They were an excessive metal method of creating a metal object without having to use a foundry. And what I realized is that the two could be combined. So I set off on a quest to combine precious metal clays and 3D printing, essentially. And I wasn't the only person that went on this quest, but most people went in a different direction. So at the time, there were a handful of 3D printers that were developed that worked on more like a syringe. And people would take the powdered metals and mix it into a slurry and then use a 3D printer to lay it out with a syringe. And my problem with that was that it required a specific 3D printer. And my quest was to make this accessible by making it work on the technology that was already available to everybody. Didn't make sense to me to have to develop a new 3D printer that just wasn't necessary. So quite simply, I bought some powdered copper and started blending it with PLA. And it took much longer than I expected, but I was able to develop a filament that's easy to use. It can be handled. It'll work in just about any 3D printer and can be processed into a pure metal object with simple off-the-shelf equipment.
Now, I can imagine that you could not imagine everything that your invention was going to be doing. And we hear about a lot of truly innovative ideas that this technology supports. In fact, students and professors all over the world are continuously publishing paper after paper about the impact this technology can have. So tell us about some that have stood out to you.
Yeah, some of the most interesting are applications in green energy. And this is exciting partly because it's a topic that I find to be very interesting. And having an opportunity to have an impact on the green energy movement is really, really important to me. And of the papers that are published, we've lost count. There's dozens, but a good portion of them go back to green energy. And interestingly, it goes back to different applications for electrolysis. So people are 3D printing electrodes, but the electrodes, what I think is interesting is that I started with electroplating and it went full circle. So now we're back to where people are using the filament to print electrodes to develop systems for hydrogen fuel cells. Ammonia generation is another interesting one. So fertilizers, and these are massive topics, and they keep becoming more and more interesting. So electrolysis is a recurring theme in the topic, and just creating parts is obviously a recurring theme.
Now, as we were preparing for our conversation today, you said a bunch of words that start with electrochemistry, electrocatalysts, electrolytes. Tell us a little bit more about how that works and how this technology supports those efforts.
Probably the easiest example to understand is hydrogen and a fuel cell. Water is made of, it's H2O, so it's 2 parts hydrogen and 1 part oxygen. To break the bond to the atomic bond, all you have to do is add a little bit of electricity to it, and they'll come into 2 separate parts. It will break into hydrogen and oxygen. And what's important about it is the energy that you put into it to separate them can be retrieved by combining them back together. So you can take energy from a solar cell that was stored during the day, use it to generate hydrogen that you store. At the end of the day, after the sun goes down, you can put it into a hydrogen fuel cell, recombine it, and then recollect the electricity that you harvested from the sun earlier in the day. And this is a very common use in chemistry, electrochemistry, I guess you would technically call it. But it's very important. The shapes, the electrodes, all those kind of things need to be very, very specific and designed in a very, very careful way. And before 3D printing, this was prohibitive. There was just no good way to form these things. But now it's simple, and you can do it with a printer that costs $500.
And along with the massive array of shapes that 3D printing allows is topological optimization. And we talked about that being applied to thermodynamics and heat transfer equipment.
Yeah, and this is a really exciting topic. This is where artificial intelligence intersects with physical objects. So in the same way that nature would form a tree, you can have artificial intelligence generate an object for you, and it'll only put material where it's necessary. So we're sort of mathematically recreating nature, and this is having these interesting secondary effects where we can create highly efficient heat sinks, heat transfer units. We can do, we can work with electricity in an induction format in ways that we couldn't before. It's always been two-dimensional. So with 3D printing, we can now create electrical coils that aren't two-dimensional. So things become much more elaborate, much more efficient. And the gap between electricity and electromagnetism gets blurred. They're almost the same thing. So blurred isn't quite the right word, but 3D printing gives you very efficient methods of dealing with non-planar induction technologies. This is exploding quickly. We have a group that's working on a fully 3D printed electric motor that will be using our iron product.
That's awesome. Another recurring theme that we're seeing in these papers is multi-material manufacturing.
Yes. Yeah, and the one that I just mentioned is a good example. So a really, really good motor will have layers of iron that are separated by an insulator. So with 3D printing, you can just lay down a layer of iron, a layer of ceramic, a layer of iron, a layer of ceramic. And you can do this. Nearly every motor that you look at, the inductors in it will be two-dimensional. They're just flat plates. But with 3D printing, you can create the unique shapes, things that are interesting and that are more efficient. So yeah, so multi-material manufacturing is one of the key advantages of metal 3D printing.
Another hot topic around here is radiation shielding. So we've got a rapid 3D shield tungsten filament, which serves as a 3D printable, non-toxic replacement for lead in radiation shielding applications. So that means you can 3D print a radiation shield in whatever custom shape that you need on the spot.
Yeah, and this is interesting, and we're finding applications in nuclear power plants. So they may need to shield a specific part quickly, and failing to do so can cause the systems to go offline. So you're in a situation where time is priceless. So this is an excellent example of where you can quickly create a part that has the properties of lead, but you're 3D printing it, and you can create it on the fly to the specifications of CAD models.
You're printing that in your regular off-the-shelf FFF 3D printer. And one really nice benefit of that material is that it doesn't have to go through that heating, debinding sinter process in order to provide that shielding benefit. So that material becomes even more accessible because of that aspect of it. Now, another topic that comes up regularly and is my personal favorite is Offplanet Research.
Yeah.
Talk about that a little bit.
Yeah, this is one that I didn't see coming, and I don't think anyone could have. But as it turns out, the lunar regolith, the dust that's already on the moon, sinters as well as the metals that we talk about. So in the same way that I created a 3D printable copper using powder, you can do the same thing with the soil that's already on the moon. We've gone so far as to print sort of bricks that can be used for landing pads on the moon, They've done tests where they put these under rocket engines to see how they held up, and yeah, it's a chunk of rock.
That is my personal favorite. I love the off-planet stuff, all the stuff happening in space, all the stuff happening on the moon. It's super cool. So you'll be hearing definitely more about that product, that 3D printing filament that Brad mentioned, and these projects in general as we go forward into the future here. Now we are adding more papers to the list on our website as they are published. You'll find a link to that webpage in the description of this video, but it's in the research and white papers is what the name is called of the page on our website. You can also use the search function on the website to look for papers. Now it's all about innovation. That's why FFF Metal is so important. You won't really hear us talking about production volumes and how to get the most parts out of the system. We will be happy to talk to you about how to scale your system if that's what you want to do. But you will hear us talk all the time about new stuff that you can do with this new technology. With custom material options, we've made molybdenum and bismuth 3D printing filaments for our customers, for example, and total control over the whole process. Innovators like you are moving the needle in so many important ways. Brad, what do you love about working with FFF Metal?
The people that we encounter, this has been it's been an incredible experience. We deal with people all over the globe every day. We have meetings where I have to ask people where they're from because I'm not even sure quite what I'm walking into. But we're meeting innovators that are looking to do things that have never been done before, and it's just been a very interesting experience.
Yes, I agree. Part of what I love about this work is working with people all over the world, all throughout the US, hearing about their ideas and looking for ways that we can help them accomplish those ideas and make impactful change on their world and on the world in general. It's a very exciting industry to be in.
It is.
Now, Brad, I do have one more very important question for you before we wrap up our conversation today.
Okay.
What happened to the man who stole a calendar?
I can't imagine.
He got 12 months.
Nice.
Now, hey, do you have a cool project that you would like to showcase in this format on one of these podcasts? Reach out to me at info@thevirtualfoundry.com. Or if you have a topic request, something you'd like us to do a deep dive on, reach out again, info@thevirtualfoundry.com. We would love to do a podcast episode with or for you. Look for us on all your favorite social channels. Be sure to like and subscribe the YouTube channel as well. And until next time, happy printing, everybody.
Thanks, everybody. My beard is trimmed crooked.
Sorry about that. People were delivering something to our house.
And we have regular lights and walls, and we flip switches and the lights come on.